Okay, we're continuing to work with our logistic growth functions. We've looked at graphing, now we're going to look at actually writing one. So we've looked at writing equations of lines, we've looked at writing equations of parabolas. Now we're going to look at writing an equation of a logistic growth function. So one, we always need to know the basic form. So our basic form is this. F of x equals, in the numerator, that's c value. In the denominator, we're going to go with our most basic form without the e. So 1 plus a times b to the x. That's our basic logistic growth function. We got to take the information we're given and put that in. So one of the things that we know is c, from up here, c is exactly the limit to growth. So here we're told the limit to growth. The maximum growth you can have is 20. So we're going to put 20 in as c. Okay, that is our limit to growth. So that's a direct, just plug it in. So we know that f of x is equal to 20 over 1 plus a times b to the x. Okay, that's a nice quick one. Now, we're going to start taking everything else that we have. An initial value is always a good place to start. It was our start for when we were looking at our exponential functions. So next thing we're going to do, so that's 1. Step 2, start that initial value. Okay, and so we know the initial value in this case is 6, which means when you have x of 0, the value of the function is 6. We've seen this a lot when we were writing our polynomials. Okay, here we're going to put in our value of our function as 6. We're putting in everything else stays the same except we're going to put 0 in for x. Okay. The nice thing about an x value of 0 being in the exponent, that means this term, that b to the 0, is 1. So we get 6 equals 20 over 1 plus a times 1, or just a. And now we just need to take a moment and solve for a. Cross multiply, or multiply both sides by 1 plus a. Why don't you try it? Solve for a. I'm going to do it so you can pause it and then come back and just check your work. All right, so if I do this by cross multiplication, I have 6 distributed times 1 plus a, so 6 plus 6a equals 20. Okay, solving for a, I get 6a equals 14. And if I divide by 6, I get a is 7/3. Okay, so now we know a. We're almost there. We've got our c, we've got our a. We just need that b. Okay, obviously then we have to use our last piece of information. Okay, our last piece of information is our third step, or the fact that it passes through the point 3, 15. Okay, so I'm going to put 3 in for x, 15 in for y, or the value of the function, keeping everything else in there, the a, the 20 for c. So we've got 15 for our value for our function, 20 as our c, 1 plus a, 7/3, times b to the, in this case, third power, because our x is 3. Okay. And now we've got to solve for b. So again, similarly, we're going to cross multiply. I'm going to come up and take advantage of this space up here. So I'm going to distribute 15 times the denominator to get 15 plus 7/3 times 15. 15 and 3 divide to 5. So that gives me 35. B to the third equals, cross multiplying, 20. Okay, solving, subtract 15, 35, b to the third is equal to 5. If I divide, I get b to the third equals 5 over 35, which is 1/7. And now we have the fact that b, if we want to write it in its exact form, is exactly 1/7, or the cube root. But since we're in exponential form, we're going to do this as, instead of the cube root of 1/7, we're going to write it to the 1/3 power. Okay, that's the same thing as a cube root, and we like things in exponential form for all of our functions. So what we get is finally the exponential, or the logistic function. Let me move up so we can see what we've got here. F of x equals 20 for my c over 1 plus, my a is 7/3, b is the value 1/7 to the power 1/3 to the x, so 1/3 x. Okay, a little tricky. We're going to have some practice problems to work through as we do that in class. Okay, but that is our final logistic growth function that has the given information that we had from before, the given initial value, the limit to growth, and the fact that it passes through 315. Okay, one last problem with our logistic functions, and then we are done. Okay, this next one says that we have Dallas's population modeled by a logistic model. Okay, population growth is often logistic. It starts to increase pretty quickly, and then it starts to slow down. We run out of space in the city or wherever we might be, or we run out of resources, whatever it might be, something starts to slow it down. Okay, so this is working for years since 1900, and we get our logistic growth model as given below. We want to know, when will the population be 1 million? Well, the formula that we have for the population gives us the population, so we want to know when this equals 1 million. Okay, so we need to figure out when this is equal to 1 million. So when does 1,000 or 1,301,642 over the whole denominator? When does that equal 1 million? Okay. If I'm going to try and figure out when that equals 1 million, that's a big, messy formula. We could, not yet, we can't solve by hand yet because we don't have our method for solving for a variable in the exponent. We will get there. So for now, we're going to do this on our calculator. So we're going to set it up, putting our left side into y1, our right side into y2. So I'm going to put this into my calculator. And then the whole denominator, make sure you put that in parentheses if you're not using the actual fraction form on the alpha y equals. Okay, if you need a minute, pause it to get that typed in. We want to know when that equals 1 million. So I'm going to put 1 million in my y2. 1, 2, 3, 4, 5, 6. That's good. Okay. So to figure out when they're equal, well, one, I know I need to be able to see this line y equals 1 million. If I just hit graph, I know I'm not going to be able to. So I'm going to change my window right away. I'm going to change my y values. First of all, when? Time. Time's not going to be negative for this problem. Let's go from 0 to 20 years. We'll see how long it takes. We might have to adjust that if we need to. So here, for a minimum y, maybe 900,000 up to 1,100,000. I like to give a little extra room around it so I can see the value. Now, if I see the graph, I should be able to see my line at y equals 1 million, which will come up here in just a moment. And I should be able to see the rest of my function. There's my y equals 1 million. And I should be able to see the rest of it, but I'm not. So let's see, unless it's larger than that. So there's a couple possibilities. Let me double check that I typed it in correctly. Okay, it looks good. So maybe I need to see a larger x value. So I'm going to go to my window, and I'm going to go up higher for my x values. In fact, I'm going to go ahead and go all the way to 100 for a moment. So I don't know how many years this is going to take. There we go. So that was the problem. We weren't seeing enough x values. So here we go. We see the y equals 1 million. We see part of our function, of our logistic growth function. And we want to know when it's exactly 1 million. Well, the when is our x. It's our x value. So we're going to find this intersection. Okay, first curve, it's on my logistic growth function. Second curve, it's on my y equals 1 million. And then I want to move over to give the calculator my guess. Near that intersection. And here we go, about 84.5 for my time. So t equals 84.5. Now we need to think about what that actually means. 84.5 for my time. And this is talking about years since 1900. So when will it be about 1 million? Sometime during the year 1984, 1984. Okay, that's when the population will be 1 million. All right, thanks for completing your notes, and we will see you in class.